Welcome back. Way back in episode 3.3, we talked about mixtures, and we mentioned that there were two types of mixtures. One is that of a heterogeneous mixture, and the other a homogeneous mixture. Now, if you recall, we said that the difference between the two lies in how uniformly distributed they are. That is to say, how well they are blended. A homogeneous mixture is very uniformly blended, so much so that the individual substances that make that mixture are no longer distinct once they're put together. Sweet tea minus the ice is an example of that, where we have tea and sugar going into water, but it's blended so well we can't tell the individual components apart. On the other hand, a heterogeneous mixture is not blended smoothly, and the substances that make that mixture are still distinct. We can tell the difference. We gave the example of a salad or sand that comes from Myrtle Beach. Not exactly uniformly blended, is it? One type of heterogeneous mixture is that of the suspension. A suspension is a mixture that contains particles that will settle out if they're left undisturbed. A good example of this is muddy water. If we take that water with the mud in it and we shake it up, we will distribute that mud in the water, but if we leave it undisturbed, that mud will begin to settle out, and after a while we'll have two layers, right? A layer of water and a layer of mud. Suspensions are usually characterized by being opaque. In other words, they're hard to see through. Also, generally speaking, the components of a suspension are easy to separate. With that muddy water, for instance, all we need to do is take a filter, we pour the muddy water through it, the water goes through, but the filter keeps the mud behind. Easily separated. As far as the size of particles in a suspension, we say that suspensions tend to have particles that are above 1,000 nanometers in diameter. Now, there are some suspensions that are fascinating because they can separate into a solid-like mixture on the bottom and water on the top. But when you agitate them, that solid substance will begin to flow like a liquid. We call these type of suspensions thixotropic. Toothpaste is an example of a thixotropic suspension. It flows when you squeeze it out of the tube, but then it remains in a solid state on your toothbrush. This is something that builders have to keep in mind, especially in earthquake zones, because some clays are thixotropic. So when you have an earthquake, that ground can literally flow like liquid at times. Therefore, any structures that are built on them could possibly collapse. A second type of heterogeneous mixture is that of the colloid. We said that in a suspension, the particles are larger, above 1,000 nanometers in diameter. A colloid, however, has particles that are slightly smaller. They're small enough to remain suspended in that mixture, even if they're left undisturbed for a time. Typically, we characterize colloids as having particles that are between 1 nanometer and 1,000 nanometers in diameter. And maybe a better way of describing a colloid is to call it a dispersion, because you have these particles that are dispersed in a medium. You have dispersed particles and dispersing mediums. You might be inclined to think that a colloid is a homogeneous mixture because when you look at it, it sort of does look like it's a uniform consistency. But if you got down on the molecular level and took a look, you would see that there's not a uniform sampling that occurs. Therefore, we still call it a heterogeneous mixture. We can further divide colloids into more categories, things like emulsions or foams or aerosols. For example, milk and mayonnaise are colloids. Both of these have liquid dispersed particles that are dispersed in a liquid medium. There are foam colloids. Whipped cream is a foam colloid. In the case of whipped cream, you have gas that's dispersed in a liquid medium. We could have solid aerosols or liquid aerosols. Smoke is a good example of a solid aerosol, where you have dispersed solid particles in a dispersing gas medium. Fog and clouds are examples of liquid aerosols, where you have dispersed liquid particles in a gaseous medium. All of these are different types of colloids. You might be wondering how these particles can actually stay dispersed in the medium. They do this because they have little polar or charged atomic groups on their surfaces. Those areas of charge on those particles are then attracted to the dispersing medium particles, creating sort of a layering effect that takes place. Then when those dispersed particles surrounded by the dispersing medium particles collide with one another, there's a repulsion that takes place, causing the particles in effect to remain dispersed in the medium. However, you can cause a disturbance in those electrostatic layers by stirring in an electrolyte. The electrolyte can cause a disturbance in those electrostatic layers, causing those particles to begin to clump together. And then when that happens, they get too big and they begin to settle out of the mixture. Because of the nature in which those dispersed particles with their electrostatic layers are colliding and repelling one another, they make sort of jerky random movements. This motion was actually given a name. We call it Brownian motion, named for the Scottish scientist Robert Brown, who first noticed this motion in colloids. Depending on its concentration, a colloid could be cloudy or even opaque. If it's dilute enough, though, it may appear clear like a solution. So how do we know the difference? What's to say that that colloid isn't a homogeneous solution? There is a phenomenon known as the Tyndall effect that separates colloids from solutions. What is the Tyndall effect? Well, let me show you. As you can see, I have 3 empty beakers here, and in each one I'm going to put some distilled water. In one of these beakers, I'll leave just the distilled water, but in the other 2, I'll put a solute. In the middle beaker, I'll put some sugar, and in this third beaker, I'll put just a little bit of liquid starch. The liquid starch in the water will create a colloid. Again, in the first beaker, we have just distilled water. The second one, we have the water with the sugar, and in the third one we have water and starch. Let's see how each of these beakers respond to this laser pointer. Let's try the distilled water first. You'll notice that we cannot see a beam scattered in the water. That's because there's no solutes to scatter the light in the first place. We wouldn't expect to. Now let's try the middle beaker, the one with the sugar and the water. When I activate the laser pointer, we still are not able to see the beam through the solution. The particles are too small to effectively scatter that light. But what about this third beaker? Let's see how it does. You can see now that it's almost completely transparent. If you didn't know any better, you'd think it was a solution. Well, let's test it with the laser pointer to find out for certain. Wow, you can clearly see the beam of light passing through. Whereas the solution's particles were not able to effectively scatter the light, the dispersed particles in the colloid are able to do so, thus allowing us to see the beam perfectly. And here, just to give us a little perspective, I'll put all 3 side by side so that the beam passes through all 3 simultaneously. You can get a really good idea of the contrast between them. It's important to note that colloids and suspensions, if they're dilute enough, can exhibit the Tyndall effect, but a solution, a homogeneous mixture, will not. You've probably seen the Tyndall effect and just never knew its name. If you've seen headlights passing through fog, that's an example of the Tyndall effect. Sunlight passing through clouds, the Tyndall effect. We can even use the Tyndall effect to figure out how many colloid particles there are in a suspension. Now let's get back to the other type of mixture, and that is the homogeneous mixture, otherwise known as a solution. In a homogeneous mixture or solution, you have extremely uniform distribution, blended very well, again, so that you can't make the distinction between components. As far as the particle size goes, in a solution, we're talking about particles that are smaller than 1 nanometer. You might recall that in a solution we have the solute and the solvent. The solute is the substance that's dissolved. The solvent is the substance that does the dissolving. Generally, there's more solvent than solute in a solution. And again, as we said before, when you look at a solution, you can't tell the difference between the solute and the solvent once they're put together. Most solutions are liquids, but it is possible to have gas solutions or even solid solutions. Our atmosphere is a type of gas solution in which you have oxygen, in this case the solute, being distributed in nitrogen, the solvent. You can have mixtures of states in a solution. Carbonated water is an example of a gas-liquid solution in which you have carbon dioxide, the solute, being dissolved into water, the solvent. There are all kinds of examples of liquid-liquid solutions. For example, vinegar is a solution of acetic acid, which is the solute, going into water, the solvent. We can also have solid liquid solutions like ocean water. The salt in the ocean is the solute, and the water, of course, is the solvent. There are even solid solutions. When we combine carbon, a solid, with iron, another solid, we get steel. Steel is a specific type of solid solution that we call an alloy. If we're talking about a particular type of solution, like a gas-gas solution, or a gas-liquid solution, a liquid-gas solution, and so on, we will usually be talking about the solute first. Carbonated water, therefore, with its carbon dioxide solute and water solvent, would be called a gas-liquid solution. One more thing we have to do in this section, and that is to talk about some terms we use to describe things that will blend together and things that won't blend together. If we have a substance that will dissolve readily in a solvent, we call it soluble. For example, sugar is readily dissolvable in water. It is soluble. Likewise, if we have a substance that does not dissolve well in a solvent, we call it insoluble. If we have liquids, though, we have a special term that we use if they are soluble with each other. Two liquids that dissolve well together and stay dissolved would be called miscible. Water and antifreeze blend together very well, therefore they are miscible. However, if you've ever used a salad dressing that contains oil and vinegar, you know that those two are immiscible. That is, they will not stay uniformly blended for long. They will separate shortly after they've been mixed. That's all the time we have for this video. Today we talked about mixtures, heterogeneous mixtures like suspensions and colloids, and homogeneous mixtures also known as solutions. We describe suspensions as having larger particles above 1,000 nanometers in diameter, being usually opaque, and having particles that easily settle out if they're left undisturbed. We described a colloid, however, as having smaller particles, small enough to remain suspended in a dispersing medium. We described how that happens due to the charges that remain on the surfaces of these particles, and we discussed Brownian motion as well as the Tyndall effect. Finally, we spent a little bit of time discussing homogeneous mixtures, the solution, solute in solvent. We even described the different types of solutions we encounter. I hope this video has been helpful to you and informative, but as always, if I can answer any questions for you, just let me know. Until next time, God bless.